So now we can go in, watch the steps. You can see. So this is Salsa. This is our strain scanner at ILL. We are a monochromatic instrument, so the monochromator is inside this gas mat where we select a single wavelength. And this is the primary optics. So we select the size of the beam that it's going to impact our sample. So we can align and move this sample around this measuring point with our hexapod that is designed for up to 1 ton. But as you can see, we can measure from laboratory size samples to very big samples. And there, just in front, is our detector. So our detector is positioned exactly at the reflection for the material we are measuring. So in this case, it's actually a powder additive manufactured component, and it's a thick one. So we are interested in terms of the thickness and in the stress distribution. So what we have on the secondary side is our third optic. This is defining the third dimension of the gauge volume we are measuring. So right now we are working with a 2 by 2 by 2 cubic millimeters, which is representative enough for this thickness. So we do the compromise between the spatial resolution and the acquisition time for each point of the measurement. We can go finer in 0.6 millimeters for thinner samples, because this is a very absorbing material, so we need enough signal on the detector. And the beauty of the detector is that we change for a larger area detector, so also we can get a higher signal. So together with the high flux of ILL, we can map same samples but faster. That could also enhance these in situ measurements, actually. So what we could do also is that if we need to set up something larger, we can actually displace all this hexapod farther. What we do for the alignment is that we use the cameras you can see on top and on the sides of the instrument. And this is a very precise alignment, maybe together with entry scans if we need a higher precision. But this is a very particular setup for the alignment on Salsa. Also, we have an instrument rig that we can set up on the hexapod. And yeah, so the whole setup, the beauty is that once we align the optics, we could also change the wavelength and then the takeoff angle. This is the table I'm sitting on top. This is the delta table. And then when we move for the wavelength and we want to have the best ratio to the flux, we need to move the takeoff angle. And then the whole system moves together. So the optical supports the hexapod, and then we don't need to realign. So that's the beauty of the delta table as well.
And how do you change or align the collimators?
Yeah, so this is now, this has been improved with all the new motors you can see, so top and bottom. So we have to align the height. This is pretty much fast. The translation is given because we know the focus distance of the collimator. What is very precise is the rotation alignment. So these are radial collimators. So we have calibration samples that we share with Munich and England with similar instruments. So this could be a foil or a pin material that diffracts very good and that we use for this very precise alignment. So usually this alignment is better than 10% by the ISO standard. In our case, it's usually better than 5% of the collimator size versus the motor position error of the hexapod. So that's how we do it. And then on top of that, the final gadget is the oscillation systems you can see on the top. So in the case of the primary, we oscillate because of a wavelength distribution of our monochromator, of our silicon monochromator. So this helps in this average wavelength. That's very important on the primary. we cannot work if this one is not oscillating. And then you can see on the secondary we have the same system, and this is for the peak resolution. So basically not to see the foils of the secondary collimator, we also oscillate it to get the average of the peak shape.